Right now, as you lie here, the universe is 13.8 billion years old. The light from the most distant galaxies our telescopes can detect left those galaxies before the Earth existed, before the Sun had formed, before the solar system was anything more than a slowly rotating cloud of gas and dust drifting through one arm of one ordinary galaxy. That light has been traveling toward us for longer than the Earth has been a planet. And right now, at this exact moment, it is falling quietly on the mirrors of telescopes around the world and in orbit above the atmosphere, being gathered, recorded, studied. The universe is vast beyond what any human mind can fully hold. It is ancient beyond what any human life can fully feel. And it has been doing all of this, the burning of stars, the turning of galaxies, the slow expansion of space itself, without any effort at all for 13.8 billion years. It does not need anything from you tonight. The universe is handling everything. Your only task right now is to rest. This is a journey through the most calming, most awe-inspiring, most perspective-shifting facts about the universe we live in. Not facts designed to alarm or overwhelm. Facts designed to remind you how extraordinary the cosmos is, how deep the piece of space runs, and how small and precious and temporary and real this moment is, in the middle of everything. Everything I am going to tell you is true. Every number, every scale, every detail. The universe is more extraordinary than any fiction, and it is yours to rest inside tonight. Begin with a slow breath in, all the way in, gently until your lungs are full. Hold it for just a moment, and breathe out slowly, all the way, feeling your body settle and release with the exhale. Let your jaw unclench. Let your shoulders drop. Let your hands relax. You are here. You are safe. And the universe has been running for 13.8 billion years without needing anything from you. Tonight is no different. Let us begin with scale. Because the first fact, the one that underlies everything else, is the sheer, staggering, almost incomprehensible size of the universe we inhabit. The observable universe, the region of space from which light has had time to reach us since the Big Bang, has a diameter of about 93 billion light years. 1 light year is the distance light travels in a year, moving at 300,000 kilometers per second. In a single second, light travels about 300,000 kilometers, roughly 7.5 times around the Earth. In a year, it travels about 9.46 trillion kilometers. Multiply that by 93 billion. That is the diameter of the region of the universe we can see. The nearest star to our Sun, Proxima Centauri, is about 4.24 light years away. The nearest large galaxy to our own, the Andromeda Galaxy, is about 2.5 million light years away. The Virgo cluster of galaxies, the nearest large cluster to our local group, is about 65 million light years away. And the edge of the observable universe is about 46.5 billion light years away in every direction from where you are lying. Within this observable universe, astronomers estimate there are approximately 2 trillion galaxies. 2 trillion. Each galaxy contains, on average, hundreds of billions of stars. Our own galaxy, the Milky Way, contains somewhere between 100 and 400 billion stars. There are more stars in the observable universe than there are grains of sand on all of Earth's beaches and deserts combined. It is a comparison that has been made many times but loses none of its force with repetition. Every grain of sand you have ever touched on every beach you have ever walked represents at least one star somewhere in the universe burning. And here's the relaxing part of this. Almost all of that, nearly all of it, is quiet. It is not silent in the way a library is silent, with people trying to be quiet. It is silent in the way that space is silent, which is that there is no medium for sound to travel through. Sound requires molecules to push against each other and transmit waves of pressure. In the vacuum of space, between the stars, between the galaxies, there are no molecules. There is no air. There is almost nothing. There is only the occasional particle of hydrogen, perhaps 1 atom per cubic meter in interstellar space, and the faint electromagnetic radiation of starlight passing through. The universe is, overwhelmingly, quiet, empty, and at rest. The light you see from a star is not the star as it is now. It is the star as it was when the light left it. For the nearest star, Proxima Centauri, you are seeing the star as it was 4.24 years ago. For the Andromeda Galaxy, you are seeing it as it was 2.5 million years ago, when our ancestors were early humans who had not yet left Africa. For the most distant galaxies visible in the Hubble Ultra Deep Field image, you are seeing them as they were over 13 billion years ago, when the universe was very young and galaxies were just beginning to form. Every time you look at the night sky, you are looking at the past. The present state of those stars and galaxies is unknown to us. We can only see the light that has already traveled here. This means that when you look at the night sky, you are seeing a record of history spread across the sky, every star at a different distance, showing you a different moment in the past. The sky is a time machine, pointed in all directions at once, showing you everything that happened in a sphere around our solar system over the past thousands and millions and billions of years. Let your breathing settle even deeper now. You are resting inside a time machine at the edge of everything visible and one of about 2 trillion galaxies on a small rocky planet orbiting a middle-aged star. It sounds enormous. It is enormous. And yet your body knows how to breathe without being told. Your heart knows how to beat. The systems that sustain you are working quietly and automatically, just as the universe turns quietly and automatically, without requiring your attention or your effort. The atoms in your body have a history that stretches back almost to the beginning of the universe. Almost all the hydrogen in the universe, the most common element, was created in the first few minutes after the Big Bang. The hydrogen atoms in the water in your body are almost 13.8 billion years old. They have been hydrogen atoms since almost the beginning. The heavier atoms in your body, the carbon, the oxygen, the nitrogen, the calcium in your bones, the iron in your blood, were created inside stars. When a star like the Sun or a larger star reaches the end of its life, it can eject the elements it has synthesized in its core out into space in a dramatic explosion or through its stellar wind. These elements became part of the interstellar medium, the gas and dust between the stars. When a new solar system forms, it incorporates these elements into its planets, and when life arises on one of those planets, it incorporates those same elements into its chemistry, into its proteins, into its DNA, into its cells. You are, in a literal and physical sense, made of star material. The iron that carries oxygen through your bloodstream was forged in the nuclear fires of a star that lived and died before the sun was born. The calcium that makes your bones rigid was produced in stellar interiors billions of years ago and scattered through space when those stars died. There is no metaphor here. This is chemistry and nuclear physics. You are a collection of stardust that learned to breathe and dream. And this stardust, these atoms, have been here long before you arrived in this form. And they will be here long after this particular arrangement dissolves. The atoms do not disappear. They continue. They become part of the soil, part of the water, part of other living things, part of the planet. The specific arrangement of atoms that is you, thinking these thoughts, breathing this breath, is temporary, but the atoms are essentially permanent on any human timescale. You are a temporary pattern made of permanent material, and the permanent material has been in the universe since the very beginning. This is not a sad thought. It is one of the most relaxing thoughts in the universe. You do not need to be permanent. The universe is permanent enough for both of you. Now let us think about emptiness. Because the universe is not just enormous, it is also almost entirely empty. Space between galaxies is very empty, but even within atoms, within the matter that makes up everything you can touch and see and feel, there is almost nothing. An atom consists of a nucleus containing protons and neutrons surrounded by electrons. The nucleus is extraordinarily small compared to the size of the atom. If you imagined an atom scaled up so that its nucleus was the size of a marble, the electron orbits would extend for about 1 kilometer in every direction. The atom would be a marble sitting in the center of a vast, mostly empty sphere 1 kilometer across. The electrons, those tiny negative particles, would be somewhere in that vast space, moving. The material in you, the solid matter of your body, is almost entirely empty space. The electrons and nuclei are almost nothing compared to the space between them. What you experience is solid matter, the feeling of the bed or floor beneath you, the weight of blankets, the hardness of walls, is not actually solid in the way it seems. It is the electromagnetic repulsion between the electron clouds of atoms, preventing them from passing through each other. You are not resting on a solid surface. You are resting on a force field generated by the interaction of atom clouds that are themselves mostly empty space. The universe, from the largest scale of galaxy clusters to the smallest scale of atoms, is overwhelmingly nothing, and in that nothing, the patterns that make up stars and planets and people arise for a while before dissolving back. The cosmic microwave background radiation is the oldest light in the universe. It was produced about 380,000 years after the Big Bang, when the universe had cooled enough for electrons and protons to combine into hydrogen atoms, making the universe transparent to light for the first time. The light released at that moment has been traveling through the expanding universe ever since. Stretched by the expansion of space from the hot, visible wavelength radiation of a plasma to the cool microwave radiation we detect today with radio telescopes. It fills the universe uniformly in every direction. When you use an old analog television with no signal, some of the static is caused by cosmic microwave background photons striking the antenna. Some of the oldest light in the universe is contributing to the static on old televisions. This ancient light is extraordinarily uniform, the same temperature in every direction to within about 1 part in 100,000. This uniformity tells us that the early universe was remarkably smooth and homogeneous, and the tiny variations of 1 part in 100. 00 are the seeds from which all the structure we see today, the galaxies, the clusters, the filaments, the vast cosmic web, eventually grew under the influence of gravity. Let your breathing slow again now, in the stillness. The cosmic microwave background radiation is passing through you right now, has been passing through you every moment of your life, is passing through every wall and every mountain and every ocean floor, carrying its ancient message from 380,000 years after the Big Bang. You are always, in this sense, bathed in the oldest light the universe has produced. The Milky Way, our galaxy, is a barred spiral galaxy. If you could see it from outside and above, it would look like a flattened disk with a bright central bulge and spiral arms curving outward. Our solar system is located about 26,000 light years from the center of the galaxy, roughly halfway out in one of the spiral arms called the Orion Arm. The Sun, with all its planets, orbits the center of the Milky Way at a speed of about 230 kilometers per second. At this speed, it takes about 225 to 250 million years to complete one full orbit of the galaxy. This period is called a galactic year or cosmic year. The last time the Sun was in the same position in its galactic orbit as it is today, dinosaurs had only just appeared on Earth. The center of the Milky Way, though hidden behind thick clouds of gas and dust, harbors a supermassive black hole called Sagittarius A star, with a mass of about 4 million times the mass of the Sun. Like all supermassive black holes in the centers of large galaxies, it is mostly quiet at present. The stars that orbit it most closely, called the S stars, have been observed over decades to be orbiting in tight ellipses around the black hole, moving at speeds that at their closest approach reach a few percent of the speed of light. These observations, made over 30 years by teams of astronomers at observatories in Hawaii and in Chile, provided some of the most direct evidence for the existence of black holes and earned their leaders a Nobel Prize in Physics in 2020. Black holes are one of the most extraordinary objects in the universe. They are not holes in space. They are regions of space-time where gravity is so intense that nothing, not even light, has enough velocity to escape. The boundary of this region is called the event horizon. At the event horizon, the escape velocity equals the speed of light. Inside the event horizon, escape becomes impossible. A black hole does not suck in material any more than the Sun sucks in the planets. Objects fall into black holes only if they come close enough and their trajectories bring them within the event horizon, just as objects fall into the Sun only if they lose enough of their orbital energy to drop inward. The most interesting property of black holes, from the perspective of relaxing facts about the universe, is what they do to time. Einstein's general theory of relativity predicts that time passes more slowly in a strong gravitational field than in a weaker one. This is not a metaphor, it is a measurable physical effect. GPS satellites, in orbit above most of Earth's atmosphere where gravity is slightly weaker, have clocks that run very slightly faster than clocks on Earth's surface. The GPS system must account for this relativistic time difference to maintain its accuracy. For a clock near a black hole's event horizon, where gravity is enormously stronger, time would pass much more slowly compared to a distant observer. An astronaut falling toward a black hole would not notice anything unusual from their own perspective, but a distant observer watching them would see them slow down and freeze, their image becoming ever redder and dimmer as the photons they emit take longer and longer to escape the deepening gravitational well. Time is not a fixed, universal thing. It flows at different rates, depending on how deep you are in a gravitational field and how fast you are moving. This has been verified experimentally with precision atomic clocks, with satellite systems, with observations of pulsars, and with many other tests of general relativity. The time you are experiencing right now, as you lie here, is slightly slower than the time experienced by someone on the top of a very tall mountain, and very slightly slower than the time experienced by a satellite in orbit above you. The universe has more than one clock. Every mass, every velocity, every gravitational field changes the flow of time. But all of this complexity, all of this relativistic space-time curvature, all of this quantum uncertainty is happening without making any sound that you can hear. The universe is running its immense, complex, beautiful machinery in complete electromagnetic silence, at least in the portion of the electromagnetic spectrum that your ears can detect. You are lying in the middle of a universe that is doing extraordinary things, and it is doing them quietly. Let your whole body relax now, from the top of your head downward, your forehead softening, your eyes resting gently, your jaw unclenched, your neck and shoulders settling, your arms heavy and still, your chest rising and falling with each breath, easy and natural, your belly soft, your legs heavy, your feet completely at rest, the weight of your body pressing gently into whatever surface is beneath you. This is where you are supposed to be. The Voyager 1 spacecraft was launched in September 1977 and is now the most distant human-made object in history. As of the mid-2020s, it is more than 24 billion kilometers from the Sun, traveling through interstellar space, the region beyond the influence of the solar wind, where the Sun's magnetic bubble ends and the broader interstellar medium begins. Voyager 1 crossed this boundary, called the heliopause, in 2012, becoming the first human-made object to enter interstellar space. Voyager 1 is still communicating with Earth. Its signal, transmitted at 23 watts, takes about 22 hours to travel from the spacecraft to Earth at the speed of light. The received signal is so faint that receiving it requires the large dish antennas of NASA's Deep Space Network, and the signal power when it arrives is about 2 times 10 to the power of minus 26 watts. This is 20 billion times weaker than the power used by a digital watch battery. And yet, it carries data. The spacecraft is still sending back measurements of the interstellar environment, the first in situ measurements ever made beyond the solar system. Aboard Voyager 1 is a golden record, a 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth, intended as a message to any intelligent civilization that might someday find the spacecraft. The record contains greetings in 55 human languages, 90 minutes of music from diverse cultures, and 116 images. It is a message in a bottle thrown into an ocean that is 93 billion light years across. Voyager 1 will not reach another star for about 40,000 years. The universe is that large. It is traveling at about 17 kilometers per second relative to the Sun, which sounds fast in human terms, and is extraordinarily fast by any standard of human experience, but is still a small fraction of the speed of light and covers only a tiny distance on the scale of the galaxy. The galaxy is quiet around it. The interstellar medium is quiet. The distances are so vast that Voyager 1 will travel for 40,000 years before coming close to anything. In those 40,000 years, human civilization as we know it may have changed beyond recognition. The languages on that golden record may be extinct. The institutions that built the spacecraft may be memories, but the spacecraft will still be traveling, carrying its message in the silence. Now let us think about dark matter and dark energy, because the universe has a remarkable secret. Most of it, the overwhelming majority of it, is made of things we cannot see and do not yet understand. The matter we can see, stars, planets, gas, dust, everything that emits or absorbs light, makes up only about 5% of the total energy content of the universe. The remaining 95% consists of two mysterious components. Dark matter makes up about 27%. Dark energy makes up about 68%. Dark matter is a form of matter that does not interact with electromagnetic radiation. It does not absorb light. It does not emit light. It does not reflect light. It is therefore invisible. But it has mass, and its gravitational effects are detectable. Galaxies rotate in ways that cannot be explained by the visible matter they contain. The orbital velocities of stars at the outer edges of galaxies are too fast to be explained by the gravity of visible matter alone. There must be additional mass distributed in a large halo around the galaxy, providing the gravity that keeps those outer stars in their orbits. This additional invisible mass is dark matter. We have measured its gravitational effects in galaxies and galaxy clusters, in the large-scale structure of the universe, and in the cosmic microwave background, but we do not know what it is made of. The most popular hypothesis is that it consists of as yet undiscovered particles that interact only through gravity and possibly the weak nuclear force, but do not interact electromagnetically. Experiments to detect these particles directly in deep underground laboratories designed to shield them from cosmic rays and other background radiation have been running for decades without a confirmed detection. Dark energy is even more mysterious. It is the name we give to whatever is causing the expansion of the universe to accelerate. In 1998, observations of distant type 1A supernovae, which can be used as standard candles to measure cosmic distances, revealed that the expansion of the universe is speeding up rather than slowing down as expected. The universe is expanding, and the rate of expansion is increasing. Something is driving this acceleration. We call it dark energy. It may be a property of space itself, an energy inherent in empty space that exerts a repulsive pressure, pushing everything apart. It may be something else entirely. We do not know what it is. But it makes up 68% of the universe. So the universe is 5% atoms, 27% dark matter, and 68% dark energy. The substance of which you are made, the atoms, the protons and neutrons and electrons, makes up only 5% of the universe. The rest is unknown. The universe is mostly made of things we have not yet understood. This is profoundly calming if you let it be. The universe is full of mystery, not danger, not threat, just mystery. The vast majority of what exists has not yet been named or characterized by science. We are surrounded by the unknown, and the unknown is simply resting there, doing whatever it does, pressing space apart or holding galaxies together without requiring anything of us. The Andromeda Galaxy, our nearest large galactic neighbor at about 5 million light-years away, is moving toward the Milky Way at about 110 kilometers per second. In about 4.5 billion years, the two galaxies will collide and begin to merge. This is not a catastrophic event in the way it might sound. Because galaxies are mostly empty space, even with billions of stars in each galaxy, the probability of any two individual stars actually colliding during the merger is extremely small. The stars will pass close to each other, and their gravitational interactions will gradually reorganize the two galaxies into a new, combined elliptical galaxy. Our solar system will likely be flung to a different location within this merged galaxy. The night sky, over those hundreds of millions of years of merging, will gradually fill with the stars of Andromeda, changing the patterns of the constellations beyond recognition. But this is 4.5 billion years away, longer than the current age of the Earth. In 5 billion years, the Sun will also be approaching the end of its hydrogen-burning phase. It will gradually brighten over the next few billion years, making Earth's surface hotter until liquid water can no longer be maintained. Long before the Andromeda merger, Earth will have become uninhabitable for surface life. But whatever descendants humanity or its successors have produced over those billions of years will have had ample time to find other places to live. The far future of the universe is also worth thinking about, not with dread, but with a kind of vast, peaceful perspective. The current era, in which stars are still forming and shining, is called the stelliferous era. It will last for another approximately 100 trillion years until the last red dwarf stars exhaust their hydrogen and fade. After that will come the degenerate era, when the universe contains mostly cold, dark stellar remnants, white dwarfs slowly cooling toward absolute zero, neutron stars, black holes. This era will last for an enormous span of time, up to perhaps 10 to the power of 40 years. Then will come the black hole era, when the universe contains mostly black holes, as other structures have either fallen in or evaporated. Black holes themselves slowly evaporate through Hawking radiation over immense timescales, the largest taking up to 10 to the power of 100 years to fully evaporate. After all the black holes are gone, the universe will be a cold, dark, nearly empty expanse in its final era, the dark era. All of this is so far in the future that the numbers are literally incomprehensible. 10 to the power of 100 years is a 1 followed by 100 zeros. The current age of the universe, 13.8 billion years, is a tiny, tiny fraction of that. We are in the very early morning of the universe's life. The universe has barely begun. Let your breath settle even more slowly. In, gently, out, fully. the universe has enormous amounts of time. You have all the time you need tonight. Neutron stars are among the most exotic objects in the universe. When a massive star, one with roughly 8 to 20 times the mass of the Sun, exhausts its nuclear fuel and its core collapses in a supernova explosion, the result can be a neutron star. A neutron star is an object with a mass of about 1.4 times the Sun's mass compressed into a sphere, only about 20 kilometers in diameter. The density of a neutron star is so extreme that a cubic centimeter of neutron star material would weigh about 100 million tons on Earth. A teaspoon of neutron star material would weigh more than Mount Everest. The surface gravity of a neutron star is roughly 200 billion times Earth's surface gravity. Time at its surface runs measurably slower than in space far from it. The magnetic field of a neutron star can be trillions of times stronger than Earth's. Some neutron stars, called pulsars, rotate extraordinarily rapidly, spinning dozens or even hundreds of times per second, beaming electromagnetic radiation from their magnetic poles like a lighthouse. The fastest known pulsars rotate over 700 times per second. These are solid objects, 20 kilometers across, spinning 700 times per second. The surface of such a pulsar at its equator is moving at a significant fraction of the speed of light, and yet, from Earth, a pulsar is a faint radio source. Its extraordinary rotation and its extraordinary density and its extraordinary magnetic field and its extraordinary time dilation are all happening in silence and stillness as seen from our perspective. The universe contains objects of unimaginable extremity, and they are all quiet, viewed from here. Gravitational waves are ripples in the fabric of space-time itself, produced when massive objects accelerate. Albert Einstein predicted their existence in 1916 as a consequence of his general theory of relativity, but for a century they seemed beyond any possibility of detection. Then, on September 14, 2015, the LIGO detectors, two identical instruments with arms 4 kilometers long, detected a gravitational wave produced by the merger of two black holes about 3 billion light years away. The merger produced a burst of gravitational radiation in a fraction of a second that released more power than all the stars in the observable universe combined. The wave reached Earth after traveling for 1.3 billion years. When it arrived, it stretched and compressed the LIGO arms by a distance less than 1,000th the diameter of a proton. This is about 10 to the power of minus 18 meters. The scientists measured this, and then another, and then hundreds more. The fabric of space-time is not static. It ripples and stretches and compresses. When two black holes merge, or two neutron stars spiral into each other, the ripples in space-time propagate outward at the speed of light, passing through everything, compressing and stretching space by amounts so tiny we need lasers to detect them. Right now, gravitational waves from distant mergers are passing through you, through the Earth, through every object in the solar system. They are not dangerous. They do not heat or disturb anything significantly. They pass through matter as if matter were not there, leaving the tiniest possible traces, and continuing outward. Space itself is breathing very, very slightly, and has always been breathing, and you have always been inside this breathing. The auroras of Earth, the northern and southern lights, are one of the most beautiful phenomena in the observable universe at our scale. They are produced when charged particles from the solar wind are funneled by Earth's magnetic field lines into the upper atmosphere at the poles, where they collide with oxygen and nitrogen and cause them to glow. The green, the red, the purple, the blue. The curtains and waves and coronae of light that move across the polar sky. At any given moment, aurora is happening somewhere in the world, at one pole or the other, as the solar wind blows and the magnetosphere channels it downward. It is happening right now, as you lie here, somewhere above the Arctic or Antarctic Circle, curtains of green light moving silently across a dark sky reflected in a frozen lake while the rest of the world sleeps. Let everything settle even more gently now. Your body is heavy and warm, your breathing is slow and regular, the universe is large and quiet and ancient around you. The atoms in your body are 4.5 billion years old in the case of the heavy elements, and 13.8 billion years old in the case of the hydrogen. The gravitational waves of distant mergers are passing through you. The cosmic microwave background is bathing you in ancient photons. The Voyager spacecraft is sailing through interstellar silence 24 billion kilometers away. The sun is converting 600 million tons of hydrogen to helium every second, 150 million kilometers away, providing the energy that warms your planet and powers the food that built your body. The Milky Way is rotating, completing one galactic orbit every 225 to 250 million years. The Andromeda Galaxy is approaching, 2.5 million light-years away, 110 kilometers per second, arriving in 4.5 billion years. Dark energy is pressing space apart in all directions simultaneously. Dark matter is holding galaxies together in its invisible embrace. And you are here, breathing, resting, warm, in the middle of all of it. The concept astronomers call the pale blue dot comes from a photograph taken by Voyager 1 in February 1990. At the request of the astronomer Carl Sagan, NASA commanded Voyager 1, then about 6 billion kilometers from the Sun, to turn its camera back toward the inner solar system and take a photograph of Earth. The Earth appears in this photograph as a tiny, faint point of light, a pale blue dot, barely visible against the scattered light of the Sun, occupying less than a single pixel in the image. Carl Sagan wrote about this photograph in a way that has become one of the most quoted passages in the history of science communication. He noted that this tiny dot is the only home we have ever known, that on it, all of human history has taken place. Every king and peasant, every saint and sinner, every inventor and explorer, every teacher and student, every act of courage or cruelty, every love and every loss has happened on this pale blue dot. The cosmic perspective does not make any of this less significant. It makes it more precious. We are rare, we are here, and we are sharing this small, warm, blue world together. The Great Attractor is a gravitational anomaly in space, a region of concentrated matter that our entire local supercluster of galaxies, the Laniakea supercluster, is slowly being pulled toward. The Great Attractor lies in the direction of the constellation Norma, about 250 million light-years away. It is thought to be a region where multiple galaxy clusters are converging, a knot in the cosmic web, a concentration of mass so large that it exerts a gravitational influence across hundreds of millions of light years. Our galaxy, our local group, our cluster, our supercluster, are all moving slowly toward the Great Attractor at about 600 kilometers per second. This motion was only discovered in the 1970s and 1980s when astronomers noticed that the cosmic microwave background was slightly hotter in one direction and slightly cooler in the opposite direction, revealing that the solar system and the Milky Way and everything local to us is drifting with a bulk velocity through the universe. We are moving. The Earth is orbiting the Sun. The Sun is orbiting the galaxy. The galaxy is falling with the local group toward the center of the Virgo cluster. The Virgo cluster is itself falling toward the Great Attractor, and the whole Laniatea supercluster is being tugged in the direction of an even larger concentration called the Shapley concentration, about 650 million light years away. The universe is not static. We are in motion in every direction simultaneously, and yet everything around you is still. The objects in this room are at rest with respect to you. Your body is at rest. The motions of the cosmic scale, hundreds of kilometers per second toward the Great Attractor, are not felt because everything in our local environment is moving with us. Stillness and motion are both real at different scales. Right now, at your scale, everything is still. There is one more fact that is worth carrying into sleep with you tonight. Among the most extraordinary and most calming facts about the universe, and it is this: the sun will continue to shine for approximately another 5 billion years, and that time it will provide stable, warm, continuous light and heat to this planet. 5 billion years is a number that has no emotional weight for humans. We cannot feel the difference between 1,000,000 years and 1,000,000,000. But consider that 5 billion years ago, the sun had not yet formed. The Earth did not exist. Life had not begun. The entire 4.5 billion year history of Earth, the Cambrian explosion, the age of fish, the age of dinosaurs, the ice ages, the rise of mammals, the evolution of humans, the entirety of recorded history from the first writing to the present day, all of it has happened in the time the sun has already been shining. It will shine for the same amount of time again, at least. The sun is at halftime. In the context of the sun's lifespan, all of human history is a vanishingly brief flicker. In the context of the universe's age, even the sun's lifespan is brief. And in the context of the universe's likely future, even the entire stelliferous era, all 100 trillion years of stars, is just the first morning of a day that will last forever by any human measure. You are here in the morning, the very, very early morning. Everything is still beginning. The universe is young. The stars are still shining. The galaxies are still turning. The light is still traveling. The gravitational waves are still propagating. The cosmic microwave background is still filling space. And you are here, inside all of it, small and warm and temporary and extraordinary, with a brain capable of knowing all of this, of finding it beautiful, of choosing to rest inside it for a few hours. Nothing is required of you tonight. The universe has been running for 13.8 billion years and will continue for trillions more. The stars will not go out while you sleep. The galaxy will still be turning when you wake. The ancient light will still be falling on the telescopes. The distant pulsars will still be spinning their hundreds of rotations per second. The gravitational waves from mergers that happened billions of years ago will still be passing through the planet. But before we drift fully into silence, there are a few more extraordinary facts worth carrying with you into rest. The universe contains an estimated 300 sextillion stars. That is a 3 followed by 23 zeros. 300 million stars. This number is so large it has no intuitive meaning, but here's one way to approach it. For every grain of sand on every beach and every desert on Earth, there are approximately 10,000 stars in the observable universe. The entire Sahara Desert, every grain of sand in it, multiplied by 10,000, would still not exceed the number of stars in the observable universe. Most of these stars are dim red dwarf stars, cooler and smaller than the Sun, burning their hydrogen so slowly that they will shine for trillions of years. Red dwarf stars are extraordinarily long, lived by stellar standards. Some of the oldest red dwarfs formed in the early universe and are still shining today. They will continue to shine long after the Sun has ended its life as a white dwarf and cooled into darkness. Many of these stars have planets. We now know, from telescope observations over the past 3 decades, that planets are extraordinarily common around stars. The Kepler Space Telescope, which operated from 2009 to 2018 and observed more than 150,000 stars, found that most stars have planets, and that roughly 1 in 5 Sun-like stars has a planet of roughly Earth size in the habitable zone, the range of orbital distances where liquid water could exist on the surface. If this fraction holds across the galaxy, and there is no reason to think it does not, the Milky Way alone contains somewhere between 10 and 40 billion potentially Earth-like planets in the habitable zones of their stars. In the observable universe as a whole, the number of potentially habitable worlds may exceed the number of grains of sand on Earth. We do not know if any of those worlds harbor life. We do not know if life is common or extraordinarily rare. We do not know if any civilization has achieved the ability to communicate across interstellar distances or has tried to do so. The search for extraterrestrial intelligence has been ongoing in various forms since the 1960s, listening for radio signals from other civilizations, and has not detected anything definitively artificial in origin. But the silence does not necessarily mean emptiness. The universe is vast. The search is in its infancy. The possible signals are many and varied, and we have only searched a tiny fraction of the available parameter space. The answer to whether we are alone remains unknown. What we do know is that the chemistry of life is universal. The same amino acids found in living cells on Earth have been found in meteorites that formed in the early solar system. Complex organic molecules, including sugars, have been detected in interstellar clouds. Water, the solvent that makes Earth's biochemistry possible, is one of the most common molecules in the universe. It exists as ice on comets, asteroids, the moons of the outer solar system, the polar caps of Mars, and in vast molecular clouds between the stars. The ingredients of life as we know it are scattered throughout the universe. Whether those ingredients have come together anywhere else to produce self-replicating chemistry that eventually became aware of itself is the great unanswered question. The James Webb Space Telescope, launched on December 25th, 2021, and deployed to its observing position at the Lagrange Point 2, about 1.5 million kilometers from Earth in the direction away from the Sun, has already transformed our understanding of the early universe and of exoplanet atmospheres. It is the largest, most powerful space telescope ever built, with a primary mirror 6.5 meters across. Assembled from 18 hexagonal, gold-coated beryllium segments in space, it observes primarily in the infrared, which allows it to see through dust clouds that block visible light and to detect the extremely redshifted light of the most distant galaxies, whose light has been stretched from the ultraviolet to the infrared by the expansion of the universe during the 13 billion years it has been traveling to reach us. JWST has imaged galaxies that existed when the universe was only a few 100 million years old, providing the deepest and sharpest views of the early universe ever obtained. It has detected the atmospheres of exoplanets, finding water vapor and carbon dioxide in the atmosphere of a gas giant orbiting another star, the first detection of carbon dioxide in an exoplanet's atmosphere. It has revealed unexpected structure in galaxies that were thought to be simpler, found fully formed massive galaxies in the very early universe that current theories of galaxy formation did not predict, and created images of such extraordinary clarity and beauty that they have become some of the most widely shared photographs in human history. The first full-color image from JWST, released in July 2022, showed a galaxy cluster called SMACS 0723 as a gravitational lens. The massive cluster bends the light of even more distant galaxies behind it, acting as a natural telescope and creating arcs and distorted images of galaxies that would otherwise be far too faint to detect. The image contains thousands of galaxies, each one containing hundreds of billions of stars, each with its own planets and moons and asteroids and comets and dust. Every dot, every smear, every arc of light in that image is a galaxy. The universe in that single photograph is incomprehensibly rich. The cosmic web is the large-scale structure of the universe, the arrangement of matter on the largest scales. When you map the positions of millions of galaxies across billions of light years, the distribution is not uniform. It forms a web-like structure of long filaments, vast sheets, and dense cluster nodes with enormous empty voids between them. This structure, known as the cosmic web, formed from the tiny density variations in the early universe, amplified by gravity over 13.8 billion years. Regions that were slightly denser than average attracted more matter, grew denser, and eventually collapsed into the filaments and clusters we see today. The voids, regions of below average density, emptied out as their matter drained away under gravity into the surrounding denser structures. The filaments of the cosmic web are not empty. They contain gas and galaxies that are being channeled along the filaments toward the dense cluster nodes. The clusters at the nodes are the most massive, gravitationally bound structures in the universe, containing thousands of galaxies in a sea of hot gas and dark matter. The Coma cluster, one of the nearest large galaxy clusters, contains over 1,000 galaxies and is about 300 million light-years away. Its hot intergalactic gas glows in X-rays, invisible to human eyes but detected by X-ray space telescopes. The gas is held in the cluster by the gravity of the dark matter halo that surrounds it. Between the filaments are the cosmic voids. The Boat's void, one of the largest known voids, is about 330 million light-years in diameter. Inside it, there are very few galaxies. It is mostly empty space. If you could somehow travel through the Boat's void, You would travel for hundreds of millions of light years without passing close to any significant concentration of matter. The universe has enormous empty rooms separated by walls of galaxy filaments, and within those rooms there is nothing but the thin wash of dark matter and the faint remnant of the cosmic microwave background. Contemplating this structure, this web of galaxies separated by vast voids, produced by the amplification of quantum fluctuations from the earliest instant of the universe, is one of the most meditation-inducing activities in science. The largest structures in the universe grew from the smallest possible starting point. The quantum uncertainty of the early cosmos expanded and stretched to astronomical scales. Everything large was once small. Every galaxy cluster, every filament, every vast void began as a tiny ripple in the quantum foam of the early universe. Let your breath settle even more deeply. In through the nose, slow and full. Hold for just a moment. And out through the mouth, slow and complete. Each breath you take contains molecules of nitrogen and oxygen that have been in Earth's atmosphere for billions of years. Some of the nitrogen in the air you breathe right now may have been breathed by a dinosaur. Some of the oxygen may have been produced by the first photosynthetic organisms that oxygenated Earth's atmosphere 2.4 billion years ago. The air is a commons, a shared resource that all of Earth's life has been cycling through for billions of years. The water on Earth is similarly ancient. The oceans formed from water delivered by comets and water-bearing asteroids in the early solar system, and from water released from the interior of the young Earth. The water cycle, the evaporation of water from the oceans, its transport through the atmosphere as water vapor, its condensation into rain and snow, its flow down rivers back to the sea, has been operating for about 3.8 billion years. The water molecules in any given raindrop have made this journey countless times. They have been in the ocean and in a cloud and falling as rain, and in a river and in the ocean again, millions of times over the history of the Earth. The water in your body, the water that makes up roughly 60% of your mass, has been water on Earth for almost 4 billion years. It has been in the ocean. It has been in clouds. It has been in rivers and lakes and glaciers and inside living things of 1,000 kinds. It has been borrowed temporarily from this ancient cycle that preceded you by billions of years and will continue after you. One of the most astonishing facts in all of biology and physics is that the human eye is sensitive enough to detect a single photon of light, the smallest possible unit of electromagnetic energy. In complete darkness, your photoreceptors, the rod cells in your retina, can be triggered by the absorption of a single quantum of light. This was demonstrated experimentally in 1942 and confirmed in modern experiments using single photon sources and sophisticated experimental protocols. Your eye is a single photon detector. It can respond to the minimum possible amount of light that physics allows. This sensitivity has been refined by evolution over hundreds of millions of years of life in environments where detecting a single photon, a reflection of starlight, off a predator's eye in the darkness could mean the difference between living and dying. The human visual system is, in this sense, at the physical limit of what is possible with light. When you close your eyes in darkness, The faint phosphenes and patterns you might see are not light. They are the electrical activity of the visual system itself, spontaneous firings of neurons that your brain interprets as light, even though none has arrived. But when your eye is open in a very dark place, and you perceive the faintest possible shimmer of light, that is a single photon arriving, a single quantum of the electromagnetic field, produced perhaps by a distant candle or a faint star, traveling to your retina and triggering a single molecular change in a single rhodopsin molecule in a single rod cell, initiating a cascade of electrical signals that reaches your visual cortex and produces a perception. You are connected through this single photon sensitivity to the universe in a very direct way. Light from distant stars, photons that have been traveling for centuries or millennia, can arrive at your eye and produce a perception in your mind. When you look at the stars on a clear night, some of those photons you detect are ancient. The starlight from the nearest naked eye star beyond the sun has been traveling for just over 4 years. The light from stars near the edge of naked eye visibility has been traveling for thousands of years. The faintest stars visible to the naked eye are at distances of several thousand light years. Those photons left their source when ancient civilizations were building their first cities or their first monuments. They have been traveling through space since then, and they end their journey at your retina. The universe is extraordinary. It is ancient and vast, and mostly quiet, and mostly empty, and full of mystery, and made of the same material as you. And tonight, in the small warm space where you are resting, in the middle of all of this, you are exactly where you are supposed to be. And the atoms in your body, the hydrogen that has been hydrogen since the very beginning, the carbon and oxygen and iron forged in long dead stars, will be exactly where they are now, forming the pattern that is you, breathing, resting, returning to a quieter state after the day's activity. Sleep now. The universe is very large and very quiet and very old, and in the middle of all that largeness and quietness and age, there is this moment, there is this breath, there is this warmth, there is this rest. Let the deep ambient hum of the cosmos carry you. The universe has been making this sound for 13.8 billion years. You have been here for a very short time, and tonight, for a few hours, you will be even more still than usual. Your thoughts will slow, your breathing will deepen, the day will recede, and the quiet of the universe will be right here, exactly where it has always been, surrounding everything, holding everything, ancient and patient and vast and utterly calm.